And welcome to our final video on the 3B9 note packet. And this final video isn't so much about atomic mass, but it is about the dual meaning of that number, of that decimal number in the box. It certainly is the average mass of the isotopes, the naturally occurring isotopes of the atom, which we now know how to calculate it and where it came from. But this number has another meaning entirely. This number is also how many grams of the element you would need to have 1 mole of the element. It's called the molar mass. And this number is one of the most used numbers in the entire subject of chemistry, the molar mass. Now, how can it have two meanings? Here's where the brilliant idea of chemists unified the periodic table to give that number two meanings. We learned earlier that the atomic mass is based on the atom isotope of carbon-12. In other words, 1 AMU is 1/12 of the carbon-12 atom. The mole, which is a quantity of atoms, is also based on carbon-12. A mole is the number of atoms you would have if you put 12 grams of carbon-12 on a balance. That is a mole. A mole is a quantity, the same as a dozen is a quantity. The mole is a quantity, and chemists need a very, very large quantity, as we will soon discuss. What is a mole? A mole happens to be 6.022, etc., times 10 to the 23rd. That is how many is in a mole. How many is in a dozen? 12. How many is in a mole? 602 times 10 to the 23rd. It is called Avogadro's number. The number of atoms. If we put 12 grams of carbon-12 on a balance, we would have 6022 times 10 to the 23rd atoms on the balance. It's named after Avogadro, who showed how this number could be calculated. So 12 grams is called the molar mass, the mass of 1 mole. Why do we need such a large quantity like 6022 times 10 to the 23rd? Why can't we use small quantities like a dozen? It's because in order for us to even use a balance, for a balance to read a number we can really see, such as 12 grams, there is an incredible number of atoms on it. Here's why we need that number. Chemical reactions are often expressed in symbolic form. Here we're seeing the element carbon burning in the presence of oxygen. The plus delta H, if you remember, means we're going to add heat energy. And the carbon will burn in the presence of oxygen to form carbon dioxide. On the small scale, for every 1 atom of carbon, there's no coefficient written there, but when there is a coefficient, we understand it to be 1. 1 carbon will react with 1 molecule of oxygen. We've got 2 oxygens that have joined together. That's a molecule. And it will form 1 molecule of carbon dioxide. So if I want to do this reaction, there's no way that I can practically take 1 atom of carbon and react it with 1 molecule of oxygen. I can't measure out 1 atom of carbon on a balance to know I have an atom. The balances we use in the lab, they read in grams. And if you remember, atoms are really, really small in terms of mass. For instance, the oxygen atom's mass is 2.6561 times 10 to the minus 23rd grams. Balances don't go out to that many spots. The balances we use in labs only go out like 2 or 3 places past the decimal, on the right side of the decimal. So we needed another quantity, a larger quantity that would be of a larger scale than 1 atom to 1 molecule. That larger scale is a mole. We base the mole again on carbon. So we could read this as well. If for every 1 atom we have a molecule, then for every 1 mole we need a 1 mole of molecules. 1 mole of carbon atoms will react with 1 mole of oxygen molecules. It's 1 to 1. A mole is the same quantity for anything. The way is a dozen is always a dozen is always 12. A mole is always 602 times 10 to the 23rd. So if we have one atom reacting with one molecule, I'd need a mole of atoms, 602 times 10 to the 23rd, to react with a mole of molecules, 6022 times 10 to the 23rd. So to get a mole of carbon, we already said, to get a mole of carbon, I need 12 grams if it's carbon 12. But get a mole of normal carbon, which would have all the isotopes of carbon in it. We know the average mass of the carbon atom is 1201. So if I put 1201 grams of carbon on a balance, I would have a mole. Oxygen atom is slightly larger than the carbon atom. So to have a mole of oxygen, I would need more than grams than I would of carbon. Carbon, I need 12 grams. What is a mole of oxygen? What is the mass of a mole of oxygen? Oxygen by itself, it would be 16, but this is O2. O2 has two O's in it. One O is 16. Two O's would be 32. So to get, if I have 32 grams of O2, I would have a mole of oxygen molecules. I would have 6022 times 10 to the 23rd. So now, in order to do this reaction, carbon burning in the presence of oxygen, by using this mole concept, I know the masses of substances to put on the balance. And just to be sure that we understand, the average mass of the carbon atom, which we call atomic mass, is 1201 AMUs. What is the mass of a mole of carbon? 12.01 grams. A hydrogen atom is 101 AMUs. What is a mole of hydrogen atoms? 101 grams. But hydrogen, like oxygen, is diatomic. They come in twos. So what is a mole of hydrogen molecules? 202 grams. Helium. A helium atom is 4 AMUs. If I want 6.022 times 10 to the 23rd helium atoms, I would need 4 grams because that's a mole. 4 is the molar mass. Magnesium. The magnesium atom is about twice as big as the carbon atom. How do I know? A magnesium atom, the average mass of magnesium is 2431, carbon's 12. So to have a mole of magnesium, I would need twice the mole mass of a mole here. I would need 24.31 grams to have a mole of magnesium. If I put 24.31 grams of magnesium on a balance, I would have 6022 times 10 to the 23rd magnesium atoms. I would have a mole. Germanium. The average mass of a germanium atom is 72.63 AMUs. Germanium is 6 times bigger. A germanium atom is 6 times bigger. So if I have a mole of germanium atoms, I would need 6 times the mass of carbon. 12 times 6, I would need 72.63 grams of germanium to have a mole. Look at krypton here. A krypton atom's 84.80 AMUs. The average mass of krypton's isotopes, 84.80. To have a mole of krypton, I would need 84.80 grams. The krypton atom, 7 times larger than the carbon atom's average. So my mass would also have to be 7 times larger. If each atom 7 times larger, a mole of atoms would also be 7 times more massive, 84.80 grams to have a mole of krypton. And if I have 84.80 grams, I know how many I have. I would have 6022 times 10 to the 23rd. So the whole point here is to show you that this is also, that decimal number, besides being the average mass of the isotopes, is also the mass needed to have a quantity that we call a mole. Why does it have two meanings? Because they're both based on carbon 12. Thank you for watching, and this ends our 3B 9 notes. If you have any questions on any of this, do not hesitate to get in contact with me if you need help.